Hello everyone. So we're going to look at Newton's second and third laws slightly again. I'm going to look at it through the prism of momentum, which is a slightly more formal way of dealing with it. And just to start off, we've got a few sort of things that we've mentioned before about Newton's laws. We'll kind of sort of rewrite a couple of them more formally. But here's what we've got. We've got his first law. An object will continue at its constant velocity unless acted on by a resultant force. We've got his second law, which at the moment we think of being force is mass times acceleration. And we've got his third law, which you've heard of, is every action is an equal and opposite reaction. And this third law is something that I want to kind of deal with. And this fourth law, so it's not really a law, he's not really said this, but this fourth principle, which is at play here, is that momentum is conserved. These three laws arise out of the fact that this statement here is true. This isn't, I've just listed it there as number 4, the fourth thing we kind of know. Right, it's not a law of Newton. So let's have a little think about how we can think about Newton's second law and Newton's third law in the context of momentum. So let's say we have an object, and I'm going to colour these in, and I'm not going to deal with a collision yet. I have a red object. It's got a mass of 10 kilograms, and it is travelling that way at a speed of 5 meters per second. Okay, and sometime later, what I'm going to do is I'm going to apply a force to it. I'm going to apply a force to it, and I'm going to slow it down. So I'm going to slow it down to half of its velocity. And let's say I do that over the course of, say, let's say this whole process. This takes, this takes one. Nope, I don't know why I've circled that. That's not very helpful. This happens in a time of equals, let's say, 0.5 seconds. Let's say that's what happens. Okay, I apply a force for half a second. This occurs. And let's just say, well, what does that, what are the things that we sort of can work out? Can we work out the force, and what do we get? So we can say that, F equals ma. We can say that the acceleration is going to be the change in velocity over the time. So we've got a change of 2.5 over minutes. Oh, fantastic! The acceleration is equal to 2.5 is our change in velocity over 0.5. Actually, it's minus. So that is going to equal minus 5 meters per second squared. So putting that into my force, I've got 10 lots of that, so I have minus 50 newtons. So that is what I've achieved to do this. Hurrah! This is straightforward. But let's now think of another block. Let's think of a blue block. Okay. That's a blue block, and it is stationary. It's going at 0 meters per second. It's got also a mass of 10 kilograms. I'm going to apply a force this way. And what's going to happen is, after a time of 0.5 seconds, it is also going to move that way with a velocity of 2.5 meters per second. I don't know. Oh, that wasn't necessary. So I just wanted to colour things in. So same problem, same thing, but sort of slightly reversed. This time we've got an accelerating force, but as a number we go, oh, well, I've done the same thing here. My force in this case, not red, I need the blue one because I'm trying to keep this consistent. In this case, you'd sit there and go, oh, okay, well, the force in this case is equal to plus 50 newtons. Okay, to get this one to slow down in a certain amount of time, given that the time scale of them both is equal, well, yeah, that force is just opposite to that force in terms, one's going that way with 50, the other's going that way with 50. So far, so straightforward. Well, how does this happen in this following situation? Let's achieve this by taking the red block and throwing it at the blue one, so that afterwards they stick together. Okay, so I'm going to call this block B and block A, block A. Right, now, in this case, I don't really need to worry so much about the time it takes. So what is going to happen here? Well, we know from like the conservation of momentum, if we start off with this moving with 5 meters per second, and this one is stationary, well, that means that initially we've got a momentum, initial momentum is equal to 50 kilogram meters per second, which means that final momentum has also got to equal 50 kilogram meters per second. And what we find out is that afterwards they must both be traveling that way at 2.5 meters per second. Now, I've achieved the exact same thing. Okay, my red block has slowed down by 2.5 meters per second. My blue block has sped up by 2.5 meters per second. How? Well, we've applied a force to them. Okay. Now, the first and instinctive force is the easy one. It's the one we think of this second block. Why is this sped up? Well, it's sped up in our heads. It's quite nice because it's sped up because we can imagine, oh yeah, this thing has moved into it and given it a whack. And so this has exerted a force on this one by hitting it. And because we like to often ascribe things as being something that's in motion, we go, oh, well, that's the thing exerting the force. But equally, the red one has also slowed down. So how has the red one slowed down? Well, it must have had a force acting in that direction, acting on it. And the only thing it's come into contact with has been the blue block. So that must mean the blue block must have pushed back on the red block with the same force. And because they're one object, because these objects are colliding with each other, here I sort of guessed at a time. I said, oh, let's call it 0.5 seconds so that I could get a number. But the time that this block exerts a force on this block must be exactly the same as the time that this block exerts a force on this block, because they are interacting. Okay, the time of interaction is identical for them both. The time that a force is acted on the red one must be equal to the time that force is acted on the blue one. But what we're interested in is that if the red one pushes the blue one this way with some force, well, the blue one must push that way with the same value force on that one, because if the times are the same and we need to get the same change, and we get to get this change of momentum, well, these need to be identical. This is Newton's third law. This idea that every action has an equal and opposite reaction. We often like to imagine that the thing that we see in motion is the thing that is the doer. We say this is doing the force on this one. But as a natural consequence of that, the same is true the other way. Now, this happens quite a lot, because if you run into a wall, you like to think of I ran into that wall, well done me. But you get hurt, okay? Don't believe me, go and punch your surface. It's hard. You get hurt, even though you like to think you're doing the action. The wall is pushed back on you with exactly the same force that you've pushed onto it. And this is what Newton's law, third law is. And this law comes up in lots of weird ways. Okay, for example, it comes up in the force of gravity. So there's the Earth, and there's you. The force of gravity acting on you, let's say, is 500 newtons. That's the force acting on you from the Earth. Well, what that must also mean is that you must also be pulling the Earth by, again, 500 newtons. But in this case, the masses aren't equal, okay? And so the outcome is quite different, okay? A 500 newton force, and I'm going to take g as being 10, but the acceleration due to a 500 newton force acting on a 50 kilogram person is 10 meters per second squared. But the mass of the Earth is much, much, much bigger. The acceleration due to a 500 newton force on the mass of the Earth, which is 6 times 10 to the 24 kilograms, well, is tiny. Okay, almost, I'm not even going to calculate it. It's absolutely minuscule. It's undetectable, your gravitational pull on the Earth. But it is there. Now, people often say, oh, but what if you got all the people? Let's say you put all 7 billion people, so 7 times 10 to the 9 people, in one spot and had them jump. Would the Earth move? Well, sadly not. Because even if you said, well, let's have an acceleration of the Earth due to all the people, you'd still get 7 times 10 to the 9 times 500 over 6 times 10 to the 24, which is slightly less tiny. Okay, all the people on the Earth simply won't make the Earth move if you go to one sort of spot in it. So this is the thing of Newton's third law, and people often get a bit bemused because normally people tend to mistake it for what we call the reaction force. So if you've got a person and they're sitting and they've got the force of gravity, so the force of gravity, which is 500 newtons, people often get confused with the normal reaction due to us standing on the Earth. So it's the Earth pushing back on us of 500 newtons and saying, oh, well, those two are the same force. That must be a Newton's third law pair. No, because these two forces are acting on the same object, whereas these forces, they must be acting on different objects. And this is how you spot a Newton's third law pair. They must be the same size, the same type, acting in opposite directions, and acting on different objects. So the gravitational, the equal and opposite reaction for the Earth pulling down on you is you pulling up on the Earth. It is not balancing two forces on something sort of standing up there. So any kind of examples of third laws, that's sort of how they interact. So you can have them as you can have them around a nucleus. So you could have a positive nucleus, and you can have an electron that's kind of in orbit around it. It's a very weird orbit. But you've got a Coulomb's law. So you've got an electrostatic force of attraction of the nucleus on the electron. You will have the same force from the nucleus on the nucleus from the electron itself. But much like the Earth, why doesn't the nucleus itself move? Well, this thing has a tiny mass, 9.11 times 10 to the minus 31 kilograms, whereas this, even a proton, even a singular proton, is about 2,000 times more massive. The mass of a single proton is 1.67 times 10 to the minus 27 kilograms. So that's the difference between the two. So let's sum up. So Newton's, so we can identify Newton's third law pair. So forces always come in pairs. So forces. Oh, I'm going to clean that up slightly. The forces must be 1, the same magnitude, 2, same type. So let's say gravitational contact, electrostatic, or magnetic, or whatever it is you want to say. They've got to be the same type of force. They've got the cause of them must be the same. They must act on different objects. And 4, act in opposite directions. And this caused a huge brouhaha several years ago in a year 13 paper where it gave an image which was essentially, it was like question 1. It was quite nice. It gave an image like this, and it was just like, explain why it's not a Newton's third law pair. And the memes that came out from people who were angry, saying that it was somehow a Newton's, who just didn't like the idea. But this is Newton's third law, that it's this idea that same magnitude, same type, act on different objects, act in opposite directions. Okay, now, so we're kind of getting nearly there. I've done a whole huge list of things. That's Newton's third law. Let's think about the next thing that we can, let's just think about the next thing to talk about. So, how do we deal with, yeah, let's go to here and let's deal with Newton's second law. So, okay. So F equals ma is a special case of Newton's law where mass is constant. Okay, and that mass is constant means that you're not a rocket that's losing matter, or you're not a particle that's going at nearly the speed of light or falling into a black hole, because any of those things tend to ruin F equals ma. You can't use it if you start going very, very fast. So F equals ma is not something that is is not intrinsically is not the most fundamental way of stating it. The more fundamental phrasing is okay. That force equal to the rate of change of the momentum of an object. Now, that is in many ways the same thing. So what we can write that mathematically is that force is equal to change in momentum over the time it takes for that change in momentum to take place. Okay, that is actually Newton's second law written as Newton wrote it, although he wrote it in Latin. But it's sort of the rate of change of motion of the object. Now that actually turns into F equals ma. So for a fixed mass, change in momentum is equal to final momentum minus initial momentum, okay, which therefore would give force is equal to mv minus mu over the change in time, and that actually equals m, and then you get v minus u over change in time, which is actually just equal to ma. So that actually does, the two do equate. It's the same way of stating it, but this is the fundamental thing, because what is definitely always conserved is momentum. Momentum is always conserved, whereas mass may not be. If mass is fixed, F equals ma, perfectly fine. If mass is not fixed, you would need to use F equals change in momentum over change in time. Now, let's think about this this example we had around here. And you might think, hang on, one of the problems it might be this idea here. Oh, I didn't know the time at which a collision occurred for. Now, the nice thing is that actually it generally didn't matter. But what I can see before and after collisions is I might not know, particularly if the collision is very rapid, I might not know how long a collision takes. Particularly people like Newton didn't know. They didn't have high-speed cameras that could slow things down and watch them back frame by frame by frame. So we actually end up with being able to define something quite cool. Okay, so we can define what we call the impulse of a force. Okay, so the impulse of a force is defined as the change in momentum that it causes. Good. So it's going to cause a change in momentum. And what we can do with that is go, okay, so if impulse is equal to change in momentum, and we say that the change in momentum is, and we also have the idea that force is equal to change in the momentum over the time that that force is applied for, well, that actually means that our change in momentum is also equal to a force multiplied by the length of time that force is applied for. So what this gives us is an idea that impulse is equal to the average force applied multiplied by the change in time, the time that's applied for, the average force applied for. It is possible, like via calculus, to do this slightly more formally in terms of like breaking it all into tiny things and not having to worry about average forces. But this is just a kind of another definition that comes out in Newton's thinking about it in terms of Newton's second law. It's a term, impulse. It means change in momentum, and it gives us this idea of it's equal to the average force multiplied by the change in time. So let's come up with a sort of an example putting this together. So an example. A person kicks a ball for 0.25 seconds. The ball, so let's give a mass of 0.4 kilograms, accelerates to 15 meters per second. We could say what is the average force, or what is the impulse and the average force. Okay, so we can say, okay, so at 1, so the impulse is equal to the change in momentum, so that is mv minus mu, so mv is 0.4 times 15 minus mu, oh that's nice, that's 0, and that gives us 0.4 times 15, 6. Now what's our unit? Well, we've got force, newtons, s times seconds, so impulse is newtons seconds, or you can define it because force, remember that for the newton is equal to kilogram meters per second squared, you'd get kilogram meters per second for force times a time. There you go. Average force is equal to delta p over delta t. So we've got essentially our impulse divided by the time that we've applied that for. So we've got 6 kilogram meters per second over 0.25, and we get 24 newtons. Okay, and what this, at the moment these are just terms, it's just terminology. But the thing that's important in terms of the design of devices is that we can decrease the average force we need by increasing the time for a change in momentum. So if you are trying to design safety gear, say in a car accident and things like airbags, seat belts and all that, that is fixed. If you're traveling at 30 meters per second, okay, and you're a 60 kilogram person, so you're traveling, if you're traveling 30 meters per second and you're 60 kilograms, you have to get rid of 1800 kilogram meters per second of momentum. That's got to be your impulse to stop. That is the thing you've got to lose. That isn't a fixed thing. So the difference, collisions are very rapid. If that loss of momentum happens in 0.1 seconds, well, that's a force of 18,000 newtons. That's very bad. If you're able to devise sort of safety features that bring that to a stop much more gently, let's say over, say, half a second. So what would it be if it's sort of like 1800 over 0.5 seconds? Well, that becomes 3,600 newtons. And that is a much, that's a much smaller number for what doesn't appear to be a great length of time. But in many collisions, because the length of time is so short, any increase in the length of time, even to still what appears to be a short number, has dramatic impacts on the amount of forces that are exerted. Okay, so what we're trying to do with seatbelts is to try and get this, so the time it takes for you to slow down actually gets towards the sort of the seconds, is creeping up, because then that becomes a much more survivable, those become much more survivable things. And there we go. That is our thing. So yeah, that's our momentum, and we're going to see that in action when we think about Mario Kart in the video that I'm going to post.